questions out of him due to the good questions that you asked. And now we're going to move on and listen to Ananya, who's going to be speaking about biocomputing. So, Ananya, please welcome Anya to the virtual stage.
Hello. Apologies if people have already seen this content before. I have modified it, but we shall see. First of all, I'd like to ask a question. How do you envision cybernetic organisms or cyborgs becoming a normal part of your civilization? I'd like you to think about that as I'm speaking, and if I've done my job properly, your perception should have or could change on that front. So, what is natural computation? It's the field of study you'd most likely associate with terms like I'll just carry on from where I was. There wasn't anything deep before that. Basically, natural computing is these three classes of research methods. And the difference between this and bio-inspired computing is that bio-inspired is a subset of natural computation. And there's generally a bit of confusion about what's the difference between AI and bio-inspired computing. There are close links because they both rely on research methods in machine learning, but the key differences are on their approaches to developing systems. So AI takes a creationist approach where the programmer is the creator, imbuing the system with intelligence. On the other hand, bio-inspired computing takes an evolutionary approach where it's more bottom-up and decentralized. So you're specifying a set of simple rules and organisms, and then methods of iteratively applying the rules to the organisms. These are usually programmed into a spiking neural network, which is a neural net that more closely mimics the behavior of the brain. And I'll come back to that later and go into more detail. But before that, why should we consider this area? There are lots of drawbacks, such as the fact that when we consider using natural materials for computation, the organic materials need considerable human assistance. For example, the addition of a catalyst at sensitive intervals or incubation. And on top of this, they'd need to go through considerable clinical trials before they can be released into the market, which further increases the delay. Then, even after this, there's the longevity of the materials to be considered, because proteins, which are the basis of these kind of systems, have a finite half-life. So we need to worry about whether the materials would degrade before completing a complex operation. And the biggest problem to consider is quite predictable, the pertinent ethical considerations. There is a potential for inappropriate iatrogenic steroid-like misuse of these materials, and they'd potentially result in unexpected or undesirable consequences that you couldn't predict because you've not had sufficient testing for them. And although this technology might improve the lifespan of humans or all kinds of life forms, it could result in a chain of unintended consequences that might exacerbate the problems with overpopulation. But the scariest thought is that if we can program organic material and integrate it successfully into living organisms, then so could a malicious party, meaning that they could create and spread infections that would potentially be more harmful and fatal than current pandemics. And I'm saying that during COVID, so just imagine how bad that could be. But despite all these warnings, we should carry on, obviously with care, but there are huge benefits of these systems if they can be properly implemented. For example, we're currently facing an issue with miniaturizing silicon chips because we're reaching the threshold of what's capable. But if we look at DNA as a method of data storage, then we can store about 108 terabytes in 1 gram of DNA, which is a little bit better than a silicon chip. And then after this, DNA replication is one of the most natural operations you can encounter in literally any form of life, plants, sea creatures. I don't need to go on. So replicating information stored in this form is far easier and a lot more accurate. And with energy consumption concerns at the moment, this research has massive advantages because operating with organic materials needs virtually no external power source because it relies on the change of chemical bonds. And then on the same tangent, using organic materials is more environmentally friendly when you consider disposing materials because they degrade as part of the carbon cycle and there are no toxic byproducts in the production or recycling process. So now I'm going to go through an overview of an area of research in each of these classes, starting with research inspired by nature. So here I'm coming back to the spiky neural networks, or SNNs, that I mentioned earlier. These, the innovation here is that they incorporate the concept of time with a property called the action potential. And as a result, they're considered third generation neural networks. The neurons in these networks fire very sparsely and asynchronously, firing a binary signal only when their input reaches a threshold value, which makes their mode of operation discrete, as opposed to a classical neural network, which has a continuous input and output signal. To further support the concept of time-based operation, each neuron in these SNNs reset to a resting potential that you can see, which sits below the threshold level. So because of this, when it next fires, the time at which the spike peaks depends. The time at which the spike peaks decides when the information contributes to a different calculation and which one it contributes to as well. One of the models that's most commonly used for this property is the leaky integrate and fire model, and that's the differential equation for it. Good luck understanding it. I've been reading up on this area for about 2 years now, and I'm still baffled. But if you get that, then fair enough. Moving on, this behavior ties into the property of connectivity. And this means that each neuron in each layer can, if it's fully connected, each neuron will be connected to every neuron in the previous and forthcoming layer. But with these spiky neural networks, that doesn't happen because that doesn't actually mimic the structure of neurons in the brain. Neurons in the brain are actually very sparsely connected, and that topology acts as filters, which you would have to integrate separately into a classical neural network. And in the brain, the structure is essentially such that there's a one-to-one interaction between neurons. So the sparser the connections, the more similar the spiky neural network is to our own brains, which is a bit counterintuitive, but that's what's happening. This approach produces a completely unexpected behavior from training because the involved positive and negative feedback loops and other properties are analogous to the rules of evolution, such as selection, recombination, and mutation. Here, training the system is equivalent to mimicking natural evolution by Darwinian and other selection processes, but this is on a much shorter time scale because we're taking advantage of the inherent lead time of millions of years because of mathematical models, scientific advances, and computational power. For example, natural evolution has already provided us with an almost ready template in the human body, which has already done the hard work of eliminating major mistakes over millions of years. So naturally, there are drawbacks with spiking neural networks, otherwise they'd already be the prevalent model. But our current computer hardware is not optimized for computationally intensive simulation of several differential equations. IBM has developed a neuromorphic chip called True North that has shown promise because it simulates neurons with their discrete, sparse, and spiking behavior. But obviously that hasn't really hit the market as of yet, so there are clearly some improvements to be made so far. There are also issues with supervision of the training in SNNs. Although there are various methods for unsupervised training, there's no currently known effective model for supervised training with a higher performance than current neural networks. And this is because the spikes aren't differentiable. So this diagram is the training trace of 3 different neurons. And as you can see, it's all binary, and you can't really differentiate that without major loss of information. But there are some current real-world applications for these networks in real-time audio and visual processing. So we'll see where this goes in the future. Now, moving on to the second class, which is using computers for synthesizing natural phenomena. One application here is that of artificial immune systems. These are a class of computationally intelligent, rule-based machine learning systems, and they sit at the intersection between bio-inspired computing and AI. This is one of the areas that kind of creates the confusion that I was talking about at the beginning. The possible applications of this area of research propose a complete rehaul in our approach to securing networks. Artificial immune systems, or AISs, and more specifically immunocomputing, focus on the mechanisms that proteins and immune networks use to process information, and as a result, solve complex problems, for example, defending the system. And the research here is done from 3 different perspectives. This understanding is then abstracted so that it can be applied to different problems. So one perspective is from a more biological stance, where the models are developed to better understand an organism's immune system. But the other 2 perspectives are of more interest to us because they're more computational. So the second one is quite metaphorical in that the aim is to develop algorithms, but rather than blatantly mimicking the immune system, it's used as a source of inspiration. Now, the final one comes from looking at immunocomputing very literally. The aim is to construct algorithms that mimic in vivo systems in silico, so literally synthesizing organic life. This is the perspective that could trigger a complete rehaul in the approach to cybersecurity. For example, mimicking receptors that can discriminate between self and non-self and defend against computer viruses would be revolutionary. And as computers become as widespread or more so than human life, our approach to securing them needs to start mimicking the innate defense system that has been tried and tested over millions of years, which is our own bodies. Again, as I mentioned earlier, all the hard work has been done for us. All the major mistakes have been eliminated. So why not take advantage of that? Now, I could go into more detail about the immune system and possible adaptations, but I have a feeling I'm running out of time and that's not as relevant. So basically, you can see the immune system as a network where the receptors are cells and how they trigger one another are the edges between them. But now stepping out of bio-inspired computing and looking at the final research method, the example I'm going to focus on here is DNA cryptography. So there's been plenty of research done into actually using DNA to compute complex problems. And an advantage of this is DNA can massively parallelly process anything, which also proposes then a complete rehaul in our approach to algorithms. Just like quantum computers are optimized for a certain type of algorithm, so would DNA computers, as it were. So DNA crypto is, of course, focused on securing information, and the information that you need can be recovered without revealing the whole sequence of data, because when a request is sent to a cell to create a new tissue, just the relevant strand is expanded and extracted, as you can see in this diagram. But the rest of the DNA strand isn't uncovered. It is very powerful, but then when you try to actually implement it, it does seem quite like a catch-22 situation. And here, DNA strands are essentially polymers of millions of linked nucleotides. And the nucleotides would essentially map to the encrypted information for us. These nucleotides are named after 4 different nitrogen bases. And coincidentally, 2 to the power 2 is also 4. So that seems like a natural link to be drawn. And an example of storing information in DNA would be to have each nucleotide represent a 2-digit binary number. Then the natural operations on DNA correspond to decryption, because the objective is to secure data by encrypting and keeping it secure at rest. This is a 2-stage operation, but again, I won't go into too much detail because of time. And there are immense advantages with this approach, like I said, with parallel processing. But the issue currently being tackled is that in a living organism, this is only a one-way process. So how do you stimulate the organic materials to reverse a process that shouldn't naturally be reversed? But ultimately, the technologies I've discussed here are part of the movement from the current rigid demarcation between computer and biological systems to seamlessly integrating them into one another. As we demand technology to be increasingly instinctive and adaptive, if we don't look at imitating the most natural complex systems to date, which is our own bodies, then we'll reach a threshold in the capability of computational systems. And on the flip side, as we develop computer systems more and more, we begin to expect more of ourselves. So then physical and mental enhancements will move to the form of integrating these biological materials that can be specifically programmed into our own bodies. And in fact, we're already heading there, because there are prosthetic limbs in general use that have the ability to process sensory input like touch and temperature. So now I'm going to move back to my opening question and ask again, how do you envision cyborgs becoming a normal part of our everyday life? Thank you.
Whoa, that was a seriously interesting talk. A lot to take in. I know we don't really have any time left, but I'd like to just ask one question that I can see on Discord now, because it's pretty interesting, I think. Do you have any advice for people who are interested in this field but don't know where to start learning about it? Like, what's a good starting point?
So that's essentially my situation. I have interest in this because I've got a medical background from my parents. So I just started reading materials that I could find. Like if you just have a look on any news apps, if something comes up that looks interesting, read it and then investigate that a bit more. And then if you can kind of build an understanding to a level where you can kind of throw that into an interview or something, then you will be guided into a relevant area. So my internship this past summer, I managed to kind of specifically state that this was an area of interest. So I was able to like arrange a conversation with a researcher who works on this kind of stuff. So it's basically a lot of initiative and reading around in your own time.
Oh yeah, that's brilliant though, the fact that you followed up on just the reading with actual experience in the field after talking to the right people. And I think that's a great point for people who are interested in just exploring any field, really. After you're done exploring the theoretical side, try to talk to the people who might bring you to more practical experience as well.
Yeah.
Yeah, it looks like we don't really have any other questions as it stands. We can wait for a few seconds due to the delay, but anyway, it's a bit past 7 p.m. anyway.
Yeah.
So I wouldn't wait for very long, personally. Just give it 10 seconds, and if not, then I'll make the closing remarks and close the event. Yep, so it looks like people aren't necessarily typing anything else right now. So thank you very much, Ananya. This was very interesting, and it was both kind of deep in a certain theoretical sense, but the fact that we also had some practical takeaways at the end is even better, or very, very good anyway. So thank you so much for coming to our event today. We loved having you, and yeah. So that was the second part of this STMU done. Hope you enjoyed the whole event. I personally enjoyed it. I enjoyed both the talks. I enjoyed hosting it. And yeah, stay tuned because we're working hard at CompSoc to bring you many more interesting events in the future. And yeah, in the meantime, stay safe and stay tuned to all of our channels so you can see what we're preparing for you guys. Thank you.